Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 6.2 and looking at linear systems with real eigenvalues. In our last video, we were introduced to systems of differential equations and how we could rewrite these linear systems in a matrix form. We looked at how we could verify solutions to this system of equations and what they look like. And we looked at how to write the general solution to a system of equations if we have several linearly independent solutions. In today's video, I would like to start looking at how we actually solve these systems of equations. So, in Chapter 6.2, we look at how to construct solutions of homogeneous linear systems of differential equations with constant coefficients. To construct these solutions, we will be using the eigenvalues and the eigenvectors of our coefficient matrix A. In Chapter 6.2, we will focus on the two-dimensional case for which the eigenvalues are always real numbers. In Chapter 6.3, we will look at the case when the eigenvalues and the eigenvectors are complex. So how do we find solutions to our system x prime equals ax? We will build our solutions by guessing. Oh, that's not how you spell guess. By guessing that they're of the form vector x equals e to the lambda t v. And maybe this seems like a reasonable guess because this looks very similar to an equation x prime equals 2x whose solutions looked like x equals c e to the 2t. So we would have an exponential component and then some vector. However, if this is going to be a solution, it must satisfy our differential equation. So let's evaluate in our DE. So we're going to look at the vector x prime equals ax. And let's evaluate our proposed solution. So here we'll stick in e to the alpha t times some vector. E to the alpha t times some vector. Now, on the left-hand side, we'll take our derivative. Assuming our vector v is a vector of constants, then the only function that we're going to take a derivative of is e to the lambda t. And the derivative of e to the lambda t is going to be lambda e to the lambda t times v. On the right-hand side, we're going to rewrite our multiplication as e to the lambda t times av. To solve this equation, we're going to regroup all our terms on the right-hand side of the equals sign to obtain 0 equals e to the lambda t AV minus lambda e to the lambda t V. Now what I would like to do is factor out common factors on our right-hand side. So we'll have 0 equals, maybe we can factor out the e to the lambda t on the left. And I'd also like to factor out the v, but I'll factor it out on the right. Now remember from chapter 5.3 when we looked at this, to factor out the v, we have to insert the identity matrix here. And this is allowed because recall, I times any vector is that vector. So inserting the identity matrix doesn't change equality. So maybe it'll help if we insert the identity matrix here. So we can factor out the vector v on the right, and it'll leave a minus lambda I in the parentheses. Now note, we want to know when this product is equal to 0. And I'm going to group this into two factors, e to the lambda t and a minus lambda I times v. Note that e to the lambda t, this is never 0. For any value of lambda. Which requires us to say then if this product is going to equal 0, then a minus lambda I v has to equal 0. But notice this is your eigenvalue eigenvector equation from chapter 5. So we are looking for non-trivial solutions, meaning we need to find a lambda and vector v. A non-trivial vector v, so a vector v that's not 0. But again, this is our eigenvalue eigenvector pair from chapter 5. This outlines a method for us to find solutions to our system of linear equations. We can first find our eigenvalues of the matrix A. We can then find the eigenvectors of the matrix A. And then we can write our solutions will be of the form x is equal to e to the lambda t v for each eigenpair that we find. We can then write our general solution, and our general solution will be of the form x of t is going to be a linear combination of each of our individual solutions. Now in general, we could have a system of equation with n different solution pairs. However, in Chapter 2, we will be focusing on two-dimensional solutions, or two-dimensional systems of equations. So our solutions will look more like C1 e to the lambda t v1, C2 e to the lambda t v2. So this will be the form of our solutions. Let's look at an example. Consider the linear system given here. Let's rewrite this system as a matrix equation. So part A as a matrix equation, we're going to let our vector x represent the vector of functions xy. So that on the left-hand side we have x prime, the vector, equals our coefficient matrix 1, 1, 4, 1 times our vector x. And this is our matrix equation of our system of equations. Now let's find our eigenvalues and eigenvectors. Recall we find our eigenvalues by looking at the determinant of a minus lambda I equals 0. There's an alternative approach to finding our eigenvalues as well that's presented in one of the homework questions in chapter 5.3, where they give us the equation lambda squared minus the trace of a times lambda plus the det of a. This shortcut equation only applies for 2 by 2 matrices. But it's saying if you can find the trace of your matrix, where the trace is defined as the sum of your main diagonal, this is your trace, and the determinant, then you can write your characteristic equation directly from your matrix. So this will be lambda squared minus the trace. Our trace is 2. It's the sum of that main diagonal. So minus 2 lambda plus your determinant, and your determinant is going to be your main diagonal, the product of your main diagonal, minus your off diagonal. So 1 minus 4 would be minus 3 equals 0. If you'd prefer using our previous definition or previous approach for finding your eigenvalues, then feel free to use your previous determinant for finding those. However, this is an alternative approach. Notice that our characteristic equation is factorable as lambda minus 3, lambda plus 1 equals 0, which gives us two eigenvalues. The first one, lambda 1, is equal to 3. The second, lambda 2, is equal to negative 1. Recall, it does not matter which order you write those. Okay. We now want to find our eigenvectors. To find our eigenvectors, we look at the equation a minus lambda I times some vector x is the 0 vector. And we'll do this for each of our eigenvalues. For lambda 1 equals 3, remember, when we look at the a minus lambda I, we're always subtracting lambda off of your main diagonal. So we'll subtract it off the main diagonal only, which will give us the matrix -2, 1, 4, -2. Times some vector xy has to equal the 0 vector. Now recall, our original matrix A is non-singular. The determinant is not 0. However, we're finding an eigenvalue that forces this matrix to be singular. So when we subtract 3, this new matrix must be singular. It must be that one of the columns is a multiple of another. And what we're looking for is a non-trivial vector x that produces the 0 vector. By inspection, I notice, what if we do 1 of the first column and 2 of the second column? If you do 1 times the first column and 2 times the second column, this will give you the 0 vector. Similarly, for our second eigenvalue, -1. Now recall, we're subtracting -1 off the main diagonal, but since we're subtracting a negative number, we do end up adding in this case to get 2, 1, 4, 2. Times some vector xy equals the 0 vector. And again, we're looking for a non-trivial solutions to this equation. Notice that your first column is 2 times your second column. So what if we did, 1 times the first column and -2 times the second column? Notice this will work. But remember, there is not only one eigenvector. We could have picked other vectors. I just need you to pick one. Another one could have been -1 times the first column and 2 times the second column. This would have also worked. Remember, our eigenspaces represent the infinite number of eigenvectors that we could have picked. I just need you to pick one for each equation. I'm going to use these first two since those are the first two I found. Okay. Now that we have our eigenvalues and eigenvectors, let's write our general solution. Remember, our general solution is going to be a linear combination of individual solutions. So we'll write this as x of t, c1, for our first eigenvalue 3, we'll have e to the 3t times its eigenvector 1, 2. Plus c2e to our second eigenvalue, -t times its eigenvector. And this will be what our general solution looks like. Now the last thing we're asked to do in this question, part D, was draw our phase plane. And our phase plane is going to represent graphically what our solutions look like. To draw our phase portrait, let's start by drawing our coordinate system, the XY plane. And to construct our phase portrait, we want to identify that our general solution is a linear combination of two solutions. A first solution, y1, is e to the 3t times this vector 1, 2. A second solution, y2, is e to the negative t times 1, negative 2. So let's first look at what this set of solutions are going to look like. And I represent this by first looking at our vector 1, 2. Our vector 1, 2 moves 1 in the x direction and 2 in the y direction, and it goes through this point. And a line going through that point would look something like this. Because we're taking any combination, any C1 of this solution. So if C1 is a positive number, it'll stretch us further in the direction of this line. If C1 is a negative number, it'll reflect it to the other side of our line. And now notice that e to the 3t, as time goes on, e to the 3t gets larger, which tells me if I ever have an initial value problem, an initial starting point on this line, solutions are going to tend to get larger or go further away. So solutions will move outward on our line. I'm going to represent this by writing a lambda equals 3 here to remind me what this looks like. Positive 3 tells me the solution is moving away. Similarly, for our second solution, e to the negative t, 1, negative 2, this would be a vector that's moving 1 in the x direction, negative 2 in the y direction, so here. And I'm going to draw a line through that point. And I'm going to represent that with the lambda equals negative 1. Now notice as time moves on, e to the negative t is always going to get smaller and go to 0. So if you're given an initial condition that's anywhere on this line, it's going to tend to shrink over time because of that e to the negative t. And so solutions along this line will always move towards the origin. And these are what these two solutions look like. However, our general solution says that solutions are always going to be a linear combination of these, or some combination of them. And to represent that, I noticed that if I ever had an initial condition that started maybe somewhere like here, this vector with lambda negative 1 will draw that solution towards the origin. However, as we get closer to the origin, the second solution, e to the 3t, 1, 2, is going to pull solutions in this direction. Similarly, if I had an initial condition that started somewhere out here, it would want to be pulled by the lambda negative 1 vector until some point that the other vector, lambda equals 3, will pull it in that direction. So it might look something like this. If we had an initial condition that started in this region, it'd get pulled this way until it got pulled the other way. And similarly, one up here would look like this. What I have drawn here are 4 more other typical trajectories. For what solutions might look like. As you start to gain familiarity with these phase portraits, it might be helpful to look at a phase portrait calculator. So let's go to our Canvas homepage. And one of the softwares I provided was a phase plane calculator. So let's click on this phase plane calculator. And this time let's choose system of differential equations. And let's enter our system. The system we started with was x prime is x plus y, and our second equation y prime 4x plus y. This will create our direction field for us. Now I'd like to include on here our individual solutions, and it's really hard to get our exactly in the right place. I can click on here and try and get it, but it's not actually the straight line solutions that we started with. So let's start by entering some solution points, and notice from our notes that we want to find a point that lives on the line represented with lambda equals -1. And maybe a point that lives on this line would be the point 1, -2. So let's enter the ordered pair 1, -2. Or if you want to go make this line a little further, maybe multiply it by 2 and call it 2, -4. Why is it not graphing that? Maybe because it's beyond the scope of this window that we're looking at. So maybe I won't try that one. Let's go to the other side. Maybe let's pick a point like -1, +2. So notice this gives me one of our solution vectors. Now let's pick ones that lived on the line represented by lambda equals 3. And a point that lived on this line would have been the ordered pair 1, 2. Or let's make it even smaller so it's closer to the origin. Let's put 0.1, 0.2. Or -0.1 and -0.2 for the other side. What I'm trying to draw here are what our individual solutions looked like. And now if we wanted to show what some other trajectories would look like, I can just click around and it'll show me what other solution curves may have looked like. This is what I'm asking you to be able to duplicate to be able to confirm that your phase portrait does look like we're showing here. Let's look at another example. Consider this linear system. Notice this one is already written as a matrix equation. What we're asked to do is find the eigenvalues and eigenvectors of this system, write the solution to your initial value problem, since we're given an initial condition this time, and then let's also draw the phase portrait. So let's first find our eigenvalues. To find the eigenvalues, you have two methods that you can use. You can look at the determinant of A minus lambda I equals 0, or you can look at our shortcut, the lambda squared minus the trace of our coefficient matrix A times lambda plus the determinant of A. I like using the trace determinant shortcut. So here we're going to have lambda squared minus the trace of A. Now recall the trace of A is the sum of your main diagonal. So here the trace is going to be 5. So minus 5 lambda plus your determinant. And remember, the determinant is your product of your main diagonal minus the product of your off diagonal. So it'd be 6 minus 2 is 4. Notice our characteristic quadratic, our polynomial, is factorable as lambda minus 4 times lambda minus 1. This gives us two distinct roots, a first eigenvalue of 4 and a second eigenvalue of positive 1. Now let's go look for our eigenvectors. And to find our eigenvectors, again, we'll look at the equation a minus lambda I times some vector is the 0 vector. And we'll have to do this for each of our eigenvalues. So for our first eigenvalue of 4. Now remember, when we're looking for our eigenvectors, we're always subtracting lambda off of your main diagonal only. When we subtract lambda off of our main diagonal, I think we'll get negative 2, 2, 1, negative 1. We're looking for a non-trivial vector x, has two components, that'll give us back the 0 vector. And again, recall, our original matrix was non-singular. The determinant was non-zero. It was 4. But this eigenvalue of 4 that we're subtracting forces this matrix to be singular. This must be singular. Meaning the determinant has to be 0, or even more important, these columns are not going to be linearly independent, which means one of these columns is a multiple of the other, and we want to use that to find an eigenvector. So I'm noticing, what if we did 1 times the first column and 1 times the second column, and we added those together? That would give us the 0 vector. And so we'll take that as our first eigenvector. Similarly, for our eigenvalue of 1, again, we'll have to subtract 1 off that main diagonal. And I think when we subtract 1 off that main diagonal, we're going to get 1, 2, 1, 2. And we need to find that non-trivial vector x that'll produce the 0 vector when we multiply. And again, what I'm looking at is I'm looking at the columns of that matrix. And I'm trying to find what vector can I multiply that'll give me the 0 vector. And notice that this is always going to be singular, meaning one of the columns is a multiple of the other. And while there are an infinite number of eigenvectors that'll work, I need you to grab just one. So one of them could be if you went 2 times the first column and negative 1 times the second column. That would produce the 0 vector. And so I'll take that as our second eigenvector. Now that we have our eigenvalues and eigenvectors, we can now write our general solution. Our general solution, x of t, is going to be c1 e to the 4t times its associated eigenvector plus C2e to the 1t times its eigenvector. And this is what our general solution is going to look like. However, we were asked to solve in our problem the initial value problem. And recall, for an initial value problem, we should be able to use our initial conditions to determine what the constant C1 and C2 must be. So let's work on that now. Our initial conditions say at time 0 we want to go through the ordered pair 4, 1. This is our initial condition. And this is dependent on us seeing what happens at time 0. So let's evaluate our general solution at time 0. So here x of 0, it's great that we're using 0 because anytime we plug in 0, we know that these exponential e to the 4t and e to the 1t become 1. So when you plug in 0, we'll get C1 times our first column vector plus C2 times our second column vector. And from our initial conditions, we know this has to equal 4, 1. And we want to find solutions for this equation. While there are many techniques we could employ from Chapter 3, I like using the matrix approach. And so I'd like to write this as a coefficient matrix times a column of unknown constants C1 and C2 that equals 4, 1. Notice that what I've written here is a matrix equation of the form AX equals B. And you could use a variety of techniques for solving this equation, an RREF matrix, an inverse matrix, Cramer's rule. However, generally I like using the RREF approach. So what I would like to do now is write the augmented matrix. It starts with our coefficient matrix. And again, I like separating the right-hand side with a dotted line, but this is my stylistic choice. And then I'm going to look at the RREF of this matrix. So if you have your calculator, pull that out. And let's enter our matrix. So second matrix, let's edit. And we're going to enter a 2 by 3 matrix, 2 rows, 3 columns. Again, take a moment just to make sure you entered that matrix in correctly. In which case, let's go back to our home screen and let's ask our calculator to do some matrix calculations for us. So go to your math option. Remember, RREF is at the bottom of your list. I like hitting the up arrow to go directly to the bottom. And let's choose the RREF option. And give our calculator the matrix A that we're working on. And get our RREF form, which it provides for us as Notice from our form that this tells us that C1 has to be 2 and C2 has to be 1. This allows us to write the solution to our initial value problem as x of t 2e to the 4t times our column vector 1, 1 plus e to the t times our column vector 2, negative 1. This is the solution to our initial value problem. And now let's also include our phase portrait. Again, our phase portrait is a graphical representation of our solutions. Recall, to graph our phase portraits, we first want to graph each of the individual solutions. And one of our solutions is e to the 4t times 1, 1, the vector. A second solution is e to the t times the vector 2, negative 1. So let's first graph our individual solutions by graphing our eigenvectors. Our first eigenvector would be 1, 1. And so a solution curve would in general go through that ordered pair, but I'm going to draw an entire line through the origin. This represents one of our solutions, and it's associated with the eigenvalue of 4. And because the eigenvalue is 4, it tells us that as time goes on, e to the 4t gets larger, so that if we had any initial condition that started on this line, solutions would move away from the origin. Similarly, let's grab our second solution. Our second solution goes through the ordered pair 2, negative 1. And let's draw a line through the origin and through this point. I'm not very good at drawing lines. And this is associated with the eigenvalue of 1. And because our eigenvalue is 1, again, as time goes on, e to the t gets larger, so any initial condition that started on this line will move away from the origin. And now I want to draw some other typical trajectories, some other solution curves. Maybe even the solution curve that went through the ordered pair of our initial value problem, which was 4, 1. So 4, 1 would be probably out here somewhere. What does the solution curve look like that goes through this point? I'd like you to think of these eigenvectors, or our individual solutions, as maybe like the current in water or an air current. Your eigenvalue of 4 tells you current is moving in this direction. And relative to the current that's moving in this direction, the eigenvalue of 4 is a lot stronger. So from this point, there's a lot more wind or current pushing you in this direction than there is in this direction. I'm going to make those arrows a little bit more emphatic. The current, or the pull towards the eigenvalue of 4, is a lot stronger than the current from the eigenvalue of 1. So if you think about vectors, there's more movement parallel to the eigenvalue of 4 than there is towards the other. This tells me that solutions, in general, will move away from the origin and end up being parallel to the eigenvalue of 4. In general, your solutions are always going to be parallel to the stronger eigenvalues. So another solution might look like this. Another solution might look like this, or like this, or like this, or what different solutions might look like. They're always going to be parallel to the stronger eigenvalue. Again, as you're building confidence with yourself drawing these phase portraits, you might want to draw or use your phase portrait plotter, the program, to confirm that this is what your solutions might look like. This might also be an appropriate place for me to encourage you to look at another video on our Canvas page. And I'm going to refer to this as the introduction to the phase plane or the trace determinant plane supplements. These two give you a great idea of all of the different outcomes one could see when they look at the phase portraits. Notice how in this particular example, how solutions move away from the origin. However, in our previous example, our phase portrait looked more like this. Each of these different outcomes is predictable, and maybe knowing ahead of time what the different outcomes might be helpful. So I'm going to encourage you to look at the introduction to the phase plane supplement and the trace determinant plane supplement that are in our Canvas course. These will give you a good idea of all the different possible outcomes that you might expect these phase portraits to look like. But I'm going to let you look at that at your own, because that's considered extra material beyond the scope of our course, or is required to talk about. Let's look at another example. Consider the linear system given by this matrix equation. And actually, I'm giving you an initial value problem again. What I'd like you to do is find the eigenvalues and eigenvectors of this system, find the solution to the IVP, and draw the phase portrait. I'd like to give you a little bit of time to work on this on your own, as it very closely mimics the last example we looked at. So if you could, pause your video and work through this question. After you're done, come back and we'll see how you did. I'll see you in a little bit. Okay, we're back. I hope you paused the video and took a look at this example on your own. I'd like to work through it with you just to make sure that we agree and we get the same answer. So let's first look for our eigenvalues and eigenvectors. And again, this is probably the last time I write this, but you have two methods for approaching this. You could use our method from chapter 5, where we look at the determinant of the matrix A minus lambda I, and we find out when this is equal to 0. Or our shortcut, the equation lambda squared minus the trace of our matrix A times lambda plus the determinant of your matrix A. Which method you use, I think, is completely up to you. I like using the trace determinant approach. So here we'll have lambda squared minus the trace. And again, recall the trace is the sum of this main diagonal. Here the trace is -4. So our formula is minus the trace So we end up getting plus 4 lambda plus your determinant. Your determinant is going to be 4 minus 1 is 3. Here, our characteristic equation is factorable as lambda plus 3, lambda plus 1 equals 0, which gives us two eigenvalues, -3 and -1. Now we're going to go and look for our eigenvectors. To find our eigenvectors, we look at the equation a minus lambda I times some vector equals the 0 vector. For our first eigenvalue, lambda 1 equals -3, our matrix. Now remember, we're subtracting lambda off the main diagonal, but here lambda is negative, so we're subtracting a negative number. We're going to be adding it to get the matrix 1, 1, 1, 1 times some non-zero vector will give us the 0 vector. And again, I want to emphasize that our original matrix that we looked at before, this was non-singular. We know that because it had a non-zero determinant. There was an inverse. These columns were not multiples of each other. However, the eigenvalue -3 forces this matrix to now be singular, meaning one of these columns is a multiple of another. This allows us to be able to find our eigenvalues, our eigenvectors. And here we're looking for a vector that will produce the 0 vector when we multiply it. And I'm thinking one of the eigenvectors might be 1, -1. If you did 1 of the first column and -1 of the second column, you would get 0 back. Of course, there are other eigenvectors you could have used. Similarly, for the eigenvalue of -1, again, we're subtracting 1 off the main diagonal. But when you subtract off a negative number, we end up adding, and I think we get the matrix -1, 1, 1, -1. And we're looking for a non-trivial vector x that when we multiply, we get the 0 vector back. And by inspection, we should be able to grab an eigenvector. And we're looking at these columns, and I'm noticing, what if you did 1 of the first column and 1 of the second column and add those together? That would give you the 0 vector. This allows us to now write our general solution. Our general solution will be of the form x of t c1e to the -3t times its eigenvector 1, -1 plus c2e to the -t times its eigenvector 1, +1. This is what your general solution will look like. However, we wanted to solve an initial value problem. So here we were given the initial conditions that at time 0 we want our vector to go through 3, 1. So let's evaluate our general solution at time 0. X at time 0 is going to be, now remember when we evaluate at 0, e to the -3t turns into a 1. E to the -t turns into a 1. And so we'll get C1 times our first column plus C2 times our second column And from our initial conditions, this has to equal 3, 1. And while there's lots of ways to approach this, I'd like to write this as a matrix equation. So matrix A times a vector of unknown constants C1 and C2, that will produce 3, 1. And again, what I'd like you to know again is that this looks like a matrix equation of the form AX equals B. And we get to use any of our techniques from chapter 3 to solve this. However, I'm going to continually like to use the augmented matrix approach. It seems to be the quickest for me. So let's write our augmented matrix. And then we'll ask our calculator to rewrite this in RREF form for us. So if you have your calculator, grab that. And let's enter in our augmented matrix. Under the edit menu, let's enter our matrix 1, 1, 3, negative 1, 1, 1. Again, take that moment to make sure that you entered it correctly. And let's go back to our home screen. And we'll ask our calculator to write this in the RREF form. Here we get our RREF as this tells us that our constants that we were looking for, C1 had to be 1, C2 had to be 2, and it allows us now to write the solution to our IVP as x of t is e to the negative 3t times our first eigenvector, which was 1, negative 1, plus 2e to the negative t times our second eigenvector, which was 1, 1. This is now the solution to our initial value problem. Now the last thing we were asked to do in this question was to draw our phase portrait. So let's draw our coordinate system. Again, the way I want you to draw the phase portrait is by first identifying what your individual solutions are going to look like. Our first solution has to go through the vector 1, negative 1. So 1 in the x direction, negative 1 in the y direction. It has to go through this point. But we're going to draw an entire line through that point. And this line is associated with the eigenvalue negative 3. Similarly, our second solution has to go through the point 1, 1. So this point. And now let's draw an entire line that represents this solution. It's really helpful on these to label your eigenvalues. And what you'd like to notice is that because your eigenvalues are negative, Anytime that you have a solution or an initial condition that starts on this line, because the eigenvalue is negative, solutions will always move towards the origin. They'll shrink over time. It's because that negative eigenvalue and that negative exponent, this is going to go towards 0 as time goes on. Similarly, for e to the negative 3t, anything that lives on this line associated with negative 3 will shrink as time goes on and move towards the origin. And this is what solutions do if you live on one of these eigenvectors. But now I want to draw some solutions that might appear if you're off of these vectors. Like our solution was starting from the point 3, 1. So 3, 1 would have been here. Now at 3, 1, you want to consider the vector movement of this at this point. There is the movement from this eigenvalue negative 1 that's pulling it in this direction. There's the movement from the eigenvalue negative 3 that's pulling it in this direction. So notice there's more movement towards that direction than there is the other. It has more movement. It's faster. But both of them are moving towards the origin. So if there's more movement here, then your solution should look something like this. It'll move faster in that direction until it almost crashes and then comes towards the origin. Or maybe it looks like this. There's another one. Or maybe it'll look like this. Here's another one. Notice they come towards the origin, but they come in being really pulled hard by that eigenvalue of negative 3. It'll look something like that. These are what typical curves would look like for this system of equations. However, the one we were talking about, because we started at the ordered pair 3, 1, probably looks more like this one. Okay. And again, as you're building familiarity with this, you may want to use the phase portrait calculator to confirm that you are drawing these correctly. Okay, I'd like to stop this video here since we're at about an hour. There's a couple more examples I'd like to do for you, but I'm going to do that in another video. I hope this is helpful so far, and I'll see you in a little while.